Again, welcome to the third week now of class. If you have noticed, I have already sent a message outlining basically the plan of what's going to happen. I think you should have received it yesterday, of what is going to happen in this week in terms of content, in terms of assignments and things like that, and also what is due this week too. I may or may not be doing this thing in the future, so please pay attention in your campus under and when you go to the homepage, actually it shows you the assignments as they are due. So please take care of those assignments. I take the deadline seriously. I think I graded most, if not all, of the assignments that were already basically due by now, basically everything that is due. And if there is one thing left, I don't think there is, but if there is one thing, basically it's just getting its chance to be graded. Most of the times I grade Saturday, Sunday, so a lot of the things will be delayed to the weekend where I grade everything that is due prior to that date and go through them. So please make sure you have all of your assignments submitted before worst case scenario when the deadline comes in. It's a good idea to start immediately on your assignments, to have a plan of action on how to tackle that assignment, come time to it, then you deliver that plan, you answer the questions, and then you move on to other things. You have other classes too, and you have other assignments in this class. Okay, so that's in a nutshell about the message that you should have received yesterday. And I don't think that there is any other matters of other than this one. And please check the syllabus. Also, there is another new type of assignment actually too that came up, and I don't know if you have had a chance to look at it, and that is the homework assignment. From now on, you will have between 4 and 8 questions to answer in an open, basically, statement format. They might require you to do some basic calculations. If you do have questions about that, first of all, you're welcome to work together. This is not an exam. This is not a test. The point of this homework assignments is for you to understand those concepts either through practice or directly answering questions related to them. So work together. If you want me to facilitate that working together by creating a session where you guys meet online, I'll be more than happy to do so. But work together on those things. If you have a question and you're still struggling with it and it's really annoying you and somebody else explains, it doesn't matter. It's still, please do ask the questions. Do not leave it to the last day and then say, okay, this is too much for me. I cannot handle it. No, from day one, what was the question 2? What was question 3? And so on and so forth. So basically ask the questions, ask me, send me a message. Hopefully on the discussion forum there too, because somebody else might have the same question as I was saying before or can answer that question there. But do ask them. There is no question that is, if you wish, quote unquote, dumb. No, there is no such a thing. All questions are valid questions. And if there is anything that is not properly delivered to you guys, it's really my problem, not anybody else's problem. That means that there is something that I need to work on to make sure that the content is fully understood. Does this sound right? I'm not trying to preach in here. I'm just trying to come up with a plan. Yes? Good, Isaac. Very good ways. The point is, you have a new assignment. You can work together on it. You're stuck in one question or 2 questions or the entire assignment. Don't hold it back there to you. Just ask the question. Ask it whichever way you do, okay? So that we can move on, okay? And there is a deadline for that too. All of the assignments, with the exception of the quizzes, they have a rubric. So open the rubric. I know the discussion has this weird place where you go to the 3 points and open the rubric and so how the rubric is, how you're going to be graded. So you could follow the rubric basically and answer all of the assignments that is there. Other types of assignment, the rubric is below them. And basically they tell you here is how you're going to be graded on question 1. If you do this, you're going to get this grade. If you don't do this, you're going to get this grade. If you don't do none, you're going to get this much grade. So you know yourself how much grade you're going to get just from the rubrics. And I follow the rubrics so that you guys know, including the deadlines and all of that. In terms of Proctorio, I made the quiz, I think, using Proctorio. So you really need to teach yourself on how to do that. The reason why is because we are preparing for ourselves for exams. And the quiz right now is actually doing Proctorio, and not all the quizzes will have that. They're just to basically get you also warmed up to it too, so that you're ready for it. You don't need your camera to be turned on for the Proctorio. Am I clear on that? You don't need the camera. what is going to record is your mouse clicks on the computer. That's what is going to be recorded. It's going to close all of your other tabs, or require you that you close all of the other tabs, so that you only have the exam before you going in there, okay? Records everything. And of course, other people, what they do, they require the camera, and if you look left or right, it assumes that probably you're looking for answers somewhere else. Like I said, there is no need for the camera. You're still, be comfortable whatever you're wearing, wear whatever clothes you want to. It's not going to record your face or your clothes or anything like that. It's going to record the screen, okay? It's going to record the screen and basically make sure that you don't have any other tabs or resources open. So that's basically what this thing is, basically, in terms of that. You will need Google Chrome, though. That's basically what this thing is. So it's preparing you for the exams. Is this right? Did you guys catch this point in here for the quiz that is coming up? Yes? Okay, very good. So let's get going with the content of today's chapter, which is chapter, I forgot the numbers, I think we're 5. The point is we're using the third law of Newton. That is really where we are. Okay. So Mr. Newton came up, unless you guys have a question. No questions? Okay. So we're going to continue with the content because I'll try to make it brief, okay, again. So the content is about the third law of Newton. Mr. Newton came up with 3 laws. He says that if you understand these 3 laws fully, you should be able to solve any problem in mechanics. It doesn't matter how hard the problem is. It doesn't matter what it involves. Any problem in mechanics will be solved. The first law basically states that if an object was at rest, it's going to stay at rest. If it's under no net forces, of course, or if it was moving, it's going to continue moving in the same direction with the same velocity. The premise here, the condition in here, is that it's under no net forces. The second law, we just finished exploring it. It says that if an object is under net forces, its motion is going to change. In other words, it's going to be subject to an acceleration, and the acceleration is proportional to the force and inversely proportional to its resistance, ability to resist the change in motion, which is its inertia or its mass. So those are the 2 laws. Well, that would be great if the universe is made up of only a single object. Then we have covered our bases. Every single base would have, there is either under net forces or no net forces. That's the only 2 possibilities. And in either case, we're covered with the first law or the second law. Now, if the universe is made up more than an object, and it is, and if these objects do not interact, then we can basically back in every one of them, isolate it in its own bubble and treat it as its own universe, and either it's under a net forces or no net forces. So that solves the problem too. Now the condition is we have more than one object, and these objects interact. That's where the third law comes in. It describes the interaction between objects, how it happens. Basically, this is the statement for the third law. If 2 objects interact, there is an if in here. 2 objects interact. If one of them exerts a force on the other exerts a force that is equal in magnitude but opposite in direction. That's it. That's basically what the statement. You will hear it sometimes named as action-reaction principle, but that's the third law. The promise is the following. If you know all of these 3 laws that I just mentioned, you should be able to solve any problem or understand any problem in mechanics. It doesn't matter how difficult it is. So we should be able to finish the class after this chapter. There is no need then for anything else because we learned everything, didn't we? Okay, before we get into the next chapters, we're going to ask other questions and see basically if this laws will be enough or we'll have to have something else to explain it. So we need to motivate the rest of the book. I mean, otherwise by chapter 5 we're done. That's really doesn't mean we're going to go home and wait until December 16th and call it a semester. So there is reasons for other chapters. Okay, we're going to tackle them later on. But hold me to my word, okay? Because I told you guys that we are going to solve every single problem in mechanics if we know these 3 laws. So the question is still valid. Why do we need the rest of the book? So we should answer this question next time when we meet. And if I skip this question, please remind me, okay? Because I want you guys to hold me accountable for what I say. Does this sound right? Do we have a plan? Good. V at least, and Kyle, everybody hopefully agree that, look, we are not going to budge from chapter 5 unless we see a reason for it, because you told us if we know everything up to chapter 5, we know how to solve everything. And that's true. So why in the world do we have to go past chapter 6? You need to have full justification for it. You need to be satisfied. You need to be asking questions. You should never be shy from asking questions. Anybody who comes in and makes a claim, you should always question their motivation and tell them, okay, what was the reason for it again? Can you explain? Why do we need to do that? So you should really be entitled to a full answers to every single question you have. Yes? Okay, I promise hopefully by Thursday, I will be here. I will not be basically running away, okay? And I will face this question with you guys, okay? And hopefully you'll be satisfied that there is a reason past chapter 5. Okay. So chapter 5, again, this is basically in a nutshell what the chapter talks about. It talks about forces and interactions, okay? We have to get to that idea that objects do interact. We state the third law, which is description of how that interaction happens. And then we get into the concept of vectors. I know some of you are in my physics 11 class, and we have had a big lab on this thing in here. And we're going to get into the idea in here too. And hopefully when you guys are doing this lab, you will have a better understanding of how vectors and work and how we add them basically specifically and things like that. And then we're going to summarize all 3 laws. Basically, I did that. I mean, the slide for summarizing 3 laws, I already did that. Okay, I give you all 3 laws. But we're going to, it's not going to hurt to basically talk about that. So an interaction, it's between one thing and another. So you need 2 objects. It requires a pair of forces. One object exerts a force on the other one exerts a force on the first one. Which one exerts first? It's a matter of semantics, because the 2 forces act in the same time. You push on something, the other thing pushes back on it. So which one is action, which one is reaction? Again, it's your choice, okay? Depending on the system, actually. So depending on which one. So again, the moment there is interaction between the objects, at that point, it's a matter of which one you call action, reaction, that's up to you. But both of the values are equal in magnitude, but opposite in directions. Okay, so that's in a nutshell what it is. And we're going to give examples on that, okay? Again, in here, whenever one object exerts a force on the second object force that is equal in magnitude but opposite in direction. Yes, the hammer is hitting the nail in this case, or whatever that thing is, but so is the nail is hitting the hammer, and it's both of them with the same force. Of course, one of them will receive probably more damage, and you can visually look at it and see it, but that's because of other properties internally, but both of them subject to the same force, okay? There is a concept of momentum that we need to develop at some points, okay? So here is a question, one of the questions for today that we need to answer. So a soccer player, so remember that we have several questions, so wait until the session is over so that you can go and answer the questions on the discussion after the class. So this is question 1. A soccer player kicks a ball with 1500 Newton of force. The ball exerts a reaction force against the player's foot of equal magnitude. So the correct answer should be B. Yes, Isaac, thank you. And everybody else, yes. So the correct answer should be B, namely 1500. What is the question? Yes. So if the soccer, so question 1, either the answer is B to it, or 1500 Newton. The N in here stands for Newton. Again, that's the unit for force. You kick a ball with 1500 Newton, the ball actually kicks you back with 1500 Newton. So the same equal force, but it's in the opposite direction, okay? So some of these balls are very heavy, actually. When you kick them, especially they're coming at the right angle, they could hurt your leg. And happens to me every week again. Okay, so are we clear on this question? This is question 1. You may write it down so that you don't forget, okay? Immediately after the session is over, you can go and answer the questions or wait until the video comes out. Okay, for those who are not live with us, of course, and there are quite a few of them. So action and reaction force, one force is called the action, the other is called the reaction, are co-pairs of a single interaction. They're both talking about the same thing, okay? And you need both of them. You can't have an action by itself or a reaction by itself. They are tangled together. They're same thing. I mean, they're part of the same thing. Neither force exists without the other, are equal in strength and opposite direction, always act on different objects. You need two different objects before you have an action reaction, okay? So both of them are needed. So these are some of the basic properties of these interactions. The forces are equal in magnitude, opposite in direction. The force come in pairs. The force come in two pairs of objects, and neither can exist without the other, okay? So these are some of their properties. Here are some examples. The car pushes on the ground pushes the car forward. That is really, I mean, if you ever asked about what force moves the car forward, it's actually the friction. Because if there is no friction, the car can spin and will not be able to push on the ground, and the ground will not be able to push the car forward. So again, in this case, the action reaction is between the tire and the asphalt, and that is, one of them is providing the action, the other one is providing the reaction, and for you, it's actually the car is moving forward. I mean, it's very hard for the ground to move backward, but it is actually, but albeit it's an infinitesimal small number that is zero practically, okay? Again, this is an example for the rocket. The rocket pushes on the gas pushes, the escaping gas, that is, from the chemical reaction that's happening in the rocket. The gas pushes the rocket forward. So again, what is propelling the rocket forward, upward? It's actually the gas that is escaping from it. That's action reaction. Without the third law, we will never be able to go to the moon or anywhere else outside of the Earth. Okay? This is another question for you guys that you need to also answer. This is a question for the after class too. When you step off of a curb, Earth pulls you downward. The reaction to this force is, so you jump up and down. You go, for example, into steps, for example, 2 or 3 steps, and you jump on the ground. Of course, the Earth is pulling you down. But in this case, the reaction to this force is a slight air resistance. That is not the reaction, okay? That's an interaction between you and something else, which is the air. We're talking about between you and the Earth in this case. Non-existence in this case, there is only action. That is not true. We just said that they come in pairs. Since you are the Earth is pulling you down, the correct answer is you are also pulling on the Earth too. Okay? So in this case, yes, it should be C. So the correct answer in this case should be C. In other words, you pull the Earth with the same amount. So if your mass, for example, is, let's say, for example, 70 kilograms, the Earth is pulling you with 700 in Newton, because 70 times 10 is 700 in Newton. So that's how much the Earth is pulling on you. That is provided you have about 70 kilograms. That's a big man, okay? Then you are also pulling the Earth with the same amount. So the Earth is actually rushing to meet you. But if you calculate the displacement, and this is where the momentum comes in later on, it's so small for the Earth, it's immeasurable. You cannot measure that quantity. But for you, it's measurable. I mean, you're coming with this much distance, depending on how much you jump from. If you jump this much, that is the whole thing. The Earth probably will not budge that, because the mass of the Earth is huge compared to your mass. So if you're pushing the Earth with 700 Newton, you're pulling the Earth with 700 Newton. 700 Newton divided by the mass of the Earth, which is of the order of 10 to the power 27 kilograms. And that is simply too much, okay? So it's going to be 0.000 followed by how many zeros? 24 zeros or something. 24, I'm sorry. Did I say 24? I forgot what the mass of the Earth is. I think it's 7 to power 27, okay? Can anybody look up the number quickly for us in here? Yeah, 24. Glad I corrected. This is the mass of the sun. A mass of Jupiter, I'm sorry. It's 10 to power 24. And you have 700 in the numerator divided by 1 followed by this many zeros, 24 zeros. So it's basically 0.0000 before you find the displacement, the acceleration. So you cannot measure this number, but it is. The correct answer is C in this case. Okay. Due to the enormous mass of don't look much evidence that you're pulling the Earth. Of course, that's basically because of the mass of the Earth is so big. Okay. Okay, so I'm going to. So basically, when you step off of a curve, didn't we ask a question on the Earth? Why do you not see the Earth moving upward? And we just answered it, because of the huge mass. It moves, but in an imperceptible amount. It's 0.0005 probably by 20 or 21 digits. I mean, 21 zeros before you reach the first digit. So that's the answer to it, okay? Because the mass of the Earth is 10 to the power 24. 6 times 10 to the power 24. 6 is nothing in this case, okay? So again, this is another example, for example, of an interaction between a big and a small, and it's similar to the interaction between you and the Earth. Again, in this case, you have a cannonball and a cannon. The cannonball usually is smaller mass, so it results in a big acceleration, whereas you have the cannon itself has a big mass, which results in a small acceleration. And there is a typo here. Hopefully you guys picked it up. It's 2 L's in this case, okay? Small. No, Weiss is asking, should we answer all of these questions? No, the questions that are only marked for the discussion, which are so far 2 questions. The first one is 1500 Newton. When you kick on the ball kicks you back with 1500 Newton, same force. And this question that we just looked at, when you pull on the Earth, when the Earth pulls you down, you pull with the same amount of the Earth, okay? Those are the only 2 questions so far, okay? Does this answer your question, Weiss? Okay, good. Okay, we might have questions outside of this ones in here so that you're... So again, this is the example of the cannonball. So a cannon is fired at the acceleration of the cannonball are different because, again, the masses are different. So you will see the cannon recoil a little, but you will see the cannonball travel far because it gave a lot of velocity compared to the cannon itself. Okay? Again, the example with the bug and the bus too, a similar one. So if there is a collision, why would since we're saying the third law, the 2 forces are equal in magnitude, but the bug gets smashed into there and goes into a smithereen versus the bus, so probably you don't even feel it until you look at it. The reason being, again, the masses play a role in this case. The forces are exactly the same, but one of them results in a tremendous acceleration, namely the bug, and so that its front probably will go with its back, and the whole thing is smashed. So tremendous acceleration, whereas the other one, the bus, doesn't feel any kind of acceleration whatsoever resulting from that collision. The force is exactly the same thing, but given the mass of the bus in this case being too much, so it's the 2 forces are the same, but the bug will suffer more damage than the bus. So again, this is more examples, 2 people of equal mass, slippery ice. So one of them pushes the other. Will both of them move at the same speed in the opposite directions? Of course they do. Okay, both of them have the same mass, equal masses though, okay? So in this case, the forces are the same, the masses are the same, the accelerations are the same, okay? There is a problem in here that needs to be clarified when we're dealing with Newton's laws in general, not just with this one, and that is the system. What do you mean? What is specifically being studied? So you really need to isolate that object for itself and then start tallying the forces as applied to that object. If a force is coming from another object outside of the system, that's an external force. If a force is between 2 objects or 2 components of the same system, those are internal forces. So there is a boundary for a system. Anything outside of the system is considered external. Anything inside is concerned internal. Newton's laws, though, they concern themselves with only the third law. I mean, concerns itself only with the internal forces, okay, of 2 objects interacting inside a system, okay. So in this case, that's what I meant for it. If an object is outside and providing an interaction with it, yes, between these 2 objects, the third law applies. But in this case, as far as this object is concerned, that is an external force coming from an object that is outside of its own system. The third law still applies in this case too. So if I have somebody is in here interacting with this one, pulling with this one, it's going to pull by an amount that is equal in magnitude. But as far as this system is concerned, that is an external force coming from an external agent. So that is actually the illustration of that. So the orange is part of the system, the apple is outside of the system. So the interaction between them, as far as the orange is concerned, as far as the system is concerned in this case, that interaction results from an external force. So this force is an external force as being applied by the apple. We don't care about the apple at this point. All we care about is the orange. That is our system. That is what we're trying to determine. As far as the apple is concerned, all it provides for us is an external force, okay? Because the apple is not the subject of the force. Whereas if we take it in this situation, both the apple and the orange are part of the same system. And these forces now are internal forces. It's still equal in magnitude in the opposite direction. But as far as the overall system, that is apple and orange, that's internal forces. External forces may still be there. For example, the force of gravity. They both or one of them could be subject to the force of gravity. Friction. They both or one of them could be subject to the force of friction, which is provided outside of the system itself. Okay, so but in either case, if one of them or both are subject to external forces, the entire system is subject to external forces. Which brings a very important point when we're dealing with problems in mechanics, and that is we have to isolate our system. We have to free our system, and we call it the free body diagram. And you will hear this thing used extensively when you're dealing with physics problems. What is the free body diagram? The free body diagram basically is take everything that is outside of the system and remove it, so that my system now is free, hence the word free, okay? But while you remove these things, you have to replace them with their effect, namely forces. So in this case, for example, I have an apple and an orange, and let's say, for example, I have the earth around them. The earth exerts gravity. So if I'm going to eliminate the earth from the picture, I have to replace it with its effect, which is the force of gravity, which is their weights. So the weights need to replace the earth. Okay, how about the friction? Is there friction? For example, between the apple and the ground, there is a friction. So in this case, if I want to eliminate the friction, namely the contact with the surface, I have to replace it with its effect. So this word, you will hear it probably sometimes, you will hear of it, especially when we're doing labs and things like that. So that's what is meant with it. You free the system by replacing with all of its things. By doing something called tally the forces. Count them. Where are they? Show me what they are, okay? Since forces are vectors, that's why you deal with vectors. That's why this concept of vectors is there, okay? So again, we're talking about friction. This is the same thing I was talking about in here. The apple and orange system will move with constant speed. If the orange loses mass, the apple gains mass. Force equal and opposite to the friction. Okay. So now we're talking about friction, okay? So both of them, the entire system now is under external forces. And for them to move with constant speed, that means the acceleration is 0. That means you have to provide a force that is equal to the force of friction, but opposite to it. So if they're moving this way, no, they're moving actually this way, the friction now has to be moving opposite to it, to the motion. So you have to provide a force equal to it in magnitude, but opposite in direction. Okay. The reason why I changed the direction of the motion is because clearly we're pointing toward where the guy is pulling. Okay. Again, the reason why they are moving as a system is because there is an external force now. Again, this is another example of action and reaction, in this case between the air and the plane. The helicopter in this case will lift off if there is a force of lift that is compensates for the force of gravity. Okay, otherwise the plane will not. If they're equal in magnitude, it's going to hover in its place. But if they change in magnitude, then it's going. If the lift is higher than the force of gravity, then it's going to take off. Okay, I'm going to trust that you guys will review some of these things. Okay, all of these questions are similar in meaning. They're all questions and examples, and if you have difficulty with them, which brings me to the concept of vectors, which I was hoping to get into, because this is part of this chapter, so you really need to have an understanding of what it is. Again, we've been talking about forces as being examples of for vectors. We talk also in terms of velocity being an example of the vector. That vector needs two things, needs a magnitude and direction. Force, for example, gravity pulls downward, always toward the center of the earth. So we know its direction and its magnitude in this case, it's equal to the mass of the object times its g times 9.8 meter per second per second. So that is the force of a gravity. The force, for example, of a spring depends on the spring itself. You pull an object on the spring and the spring will pull back against it. So it has a direction and magnitude. The force, for example, of friction, also opposite to the direction of motion or the intended direction of motion, because there are two kinds of frictions. Actually, there are more than two kinds. There is the static friction, for example, if I push on the table is actually not moving. So in this case, it's static friction. Or when the object is moving, like a moving car, for example, that is actually kinetic friction, friction of motion. So that opposes the direction of motion. And there are other kinds like the force of drag and other things that also come into play. Okay, and I think we'll talk about that. The velocity is another example of a vector because it needs direction and magnitude too. So in this case, every vector can be represented by two numbers. Okay, a magnitude plus direction. Those are the two things needed for a vector. Its magnitude and its direction, okay? Now, also, alternatively, at least on the plane, you can represent it with two other numbers, the components of the vector. By the way, the direction is always measured with respect to the horizontal direction, or the x-axis usually it's called, okay? In a Cartesian coordinate system, the plane is represented by x and y directions. So the vector in this case, the direction is how much, so this is a vector, so I'm drawing in here. What is this angle with respect to the x-axis? So that is always the direction, is with respect to the x-axis, the horizontal direction, or east-west, where east is the positive direction. So this is the east direction. Okay, this is the west direction. So always with respect to the east axis. That's by convention. Everybody agrees to that. And it goes from 0 to 90 to 180 to 270 back to 360. By the time you reach 360, you have made full circle. Okay. So now you can go 360 plus 90, which is 450, and so on and so forth. So you can do this circle as many times as you want. 450 or 90 degrees, they're the same thing. They're off only by 360, which is a full cycle. So that's in terms of direction. The magnitude is actually the length of the vector itself. When you add the vectors, probably let me open an okay, what is annotated here? No, I don't want to do that. Never mind. Anyway, because this is getting a little bit crowded, so let me get one note in here open for you guys to illustrate these points in here, because I really want to have you guys have an understanding of what this means. I know it's a repetition for those of you who are sitting in Physics 11 already, but those who are not, at least they need to benefit from the same thing. So again, we have, what happened in here? Draw. Oh, this thing. So this is an x-axis and a y-axis, and a vector has a direction. So this is a specific vector of a specific length. The length you measure it with a ruler on the plane, if you are drawing it, and the direction you measure it with a protractor. That's an angle with respect to the x-axis. Now, you want to know, for example, if I have two vectors, how am I going to add them up? Okay. Here is an example, typical example. You went camping and you traveled east, for example, 5 miles. And then you traveled north another 5 miles. Okay. How far are you from base in this case? Here is the base. Here's your starting point. It's this distance. It's not 5 plus 5. It's not 10, in this case, miles. It's this distance, that is the distance how far you are. Because if you choose to come back, if this is your starting point A, and this is B, and this is C, so if all of your goal was to go to C, you could have gone straight out and did the same thing. You ended up there. So usually, if this is a vector which is represented by an arrow, and this is another vector, it's the same thing as going directly from A to C. And that is how you add vectors. So if you give me this vector, and you want to add it to this vector, I'm going to do the parallel to it, and that is the sum of these two vectors. So this is how graphically you add the two vectors, okay? Again, they don't have to have that direction. Any other direction would do. So if this is the original vector, remember this is making an angle which is this much with the x-axis, and this is another vector. I draw the parallel to one of them, or I draw the other vector as represented from the first one, a length that is equal to this one, and parallel to it from one end, and that is the sum of these two vectors. So that's how I do it graphically, and then go with the ruler and measure this distance. Of course, I have to know exactly what my scale is, and then from there I can say this is the sum of these two vectors. And the direction actually is this direction of this vector, so I can use again protractor to measure how much angle I have, and I'm back in business. So I can tell you the sum of these two vectors using this method. You say, okay, I have more than two vectors, I have three vectors. How am I going to do that? Well, if you have more than three vectors, it's fine. Just pair them. You have one vector. This is the second vector. Add the parallel to it. So this is the second vector. Let's say, for example, for the sake of argument, you have this vector too. So you're going to subtract from it this vector, or add it this way. I'm sorry, add it still. And you're there. So this is the sum of three vectors. You pair them. You did 1 with 2. And then you added the last one 3, and this is the actual resultant. So that's basically how you add vectors, okay? You add them graphically. There is a computer method which is a little bit, it uses trig. And since you guys are not required to do that, that is something else, okay? But that's in a nutshell how you add vectors, okay? Graphically. I know it's not getting into a lot of details of how you do that, but at least giving you an idea how to do this. For those who are doing physics 11, they're probably sick of this thing because they already have seen it plenty. Anybody in here sick of it? Be honest, okay? From physics 11? No? You guys want more of this? Okay. Okay, that's fine. So let's continue with this. So that's basically, there is another way of representing vectors, and that is with the components. Components with representation is similar to the magnitude direction, and it actually involves how much we have to travel on the x-axis and how much we travel on the y-axis. That is the component method. So for example, I have in here a vector of 100, whatever the length 100 is, and the another vector of another 100, but they're making a 90-degree angle between them. And the question, that's your third question of the day that you're supposed to answer today, is what is the resultant? What is the sum of these two vectors? The word resultant means the sum. So let me try to represent it so that we are on the same thing in here. So I have 100, oops, a pen. I have 100 on the x-axis and 100 on the y-axis. Both of them are supposed to be the same length, by the way. I messed it up in here. So I want to know what is the length of their sum. If you remember, some of you probably did the Pythagorean theorem. It's the sum of this one squared, because this is a right angle triangle, okay? This is they're making a 90-degree angle. That's what I'm saying in here. So if they're making a 90-degree angle, this is a 90-degree angle, and the Pythagorean theorem, this will be the square root of 100 squared plus 100 squared. And if I use a calculator, it's going to roughly give me 141. So the second question to the third question for the day today is the sum of vector sum, not the sum. Vector sum of 100 east and 100 north is 141 north east, if you wish, at 45 degrees because an equilateral too. I mean, not equal, isosceles too, okay? Because the two sides are the same side, the 100 and 100. So the angles must be the same angles. And since one of them is 90 degrees, the other ones must be equal and add up to 90 degrees, which means that they are 45 degrees, okay? So that's the third question for you guys. So it's a vector. It needs also direction. It's not just a magnitude. So 141 is just its magnitude. Its direction in this case is 45 degrees. Now we have fully qualified that as a vector too, because we need the two numbers. Does this make sense to you guys? Okay, there were two more questions before this one, okay? Can anybody remind us of what the other two questions is? One of them was a 1500 Newton for the soccer ball, and the other one was, if I remember my notes in here. Yes, for the when you pull on the earth pulls back on you. Yep, thank you, Vanessa. Okay, thank you, Daniel, also, and everybody else. Good. So those are everything, and this is the third one. Are we in business? Everybody? Okay, so we're all together now. So let's keep on moving then. So the third question is not actually one of those multiple choice things in there that you guys have in the notes, but it's actually outside of that. Okay, so we are in additional vectors and trying to understand what the vectors are. Okay, once you have, for example, a rough idea of how the sum of the forces understand, then you can deal with problems. In this case, Nelly pulls on the sled, as shown which component of the force F is greater. Of course, in this case, from graphic, it looks like the length Fx is bigger than Fy. So it's pulling on the x-axis more than she's doing on the y-axis. From the dog perspective, though, the dog is under two forces, under its own weight, and they're also because if it's only the weight, this thing should sink. So there must be something to support it, and that is the support force coming from the ground. That is usually called the normal. But it's accelerated toward this direction if there is no friction. Let's say, for example, if there is a friction, then we have a friction involved. Okay? So if friction is involved, then there is a friction. In addition to this force in here that is provided by Nelly. So in this case, there are four forces. So when I do my so-called free body diagram, and if my object is just the dog, I want to understand the dog in this case, and the sled, both of them combined as a system, sled-dog system. So in this case, the sled-dog system is composed of the forces on it are the force of gravity. So if I remove the earth from the picture, I have to replace it by its effect, which is the weight of the dog, probably the sled also. And in addition to that, there is the reaction, the support force coming from the ground. Otherwise, this thing will sink to the ground. So the ground, I want to get rid of it. So one of its effects is the normal force, the support force. And also another effect of the ground is actually the friction too. So I'm going to plug in the friction before I remove the ground. And then finally, if I want to get rid of Nelly, I want to replace her by her effect, which was the force that she was pulling with. Now, my sled dog system is free. And it's a free body diagram. The reason why we call it diagram is it has these forces. mg in here for weight, F of friction in here, and the force provided by the external agent. So that is what we call free body diagram. So you might see it in the book. You might see it in some activities. They talk about the forces on the system. This is what is meant with it. You isolate the system completely from the rest of the universe, and by replacing their effects, the effects of the external agents that you want to remove. Then at that point, you can redraw the dog sled system as just a points in this case, with a weight, friction, normal, and the force coming from the Nelly. So that's it. Those are the 5 things. Okay? Depending on if the object is accelerating, then you put a MA on the other side. If the object now is stationary, you put 0 on the other side. Solving these equations will enable you to describe the future of this sled dog in the future completely. So empowered with the third law, because the action reaction in here with the ground is actually action reaction, because the dog and sled, they're pushing on the ground. As far as the dog and the sled, the ground is pushing up. That's where the third law comes in. The action and reaction between the dog sled and the earth is actually the force of gravity. Yes, the earth is pulling on the dog as far as the dog is concerned. That's why we included that when we removed the earth. But actually the dog also is pulling on that. So that's where the third law is coming into play in here. Yes, Nelly is pulling with them on this force, and show her they are pulling on her with this force. Case in point, if you don't believe me, cut the rope and you will see what happened to Nelly. So they're pulling her with the same force. If she keeps on pulling and you cut the rope, you know what's going to happen. So they're pulling with her on that. So now we have eliminated Nelly, we have eliminated the ground, and we have eliminated everything. And now we're going to solve this equation. Once we solve this equation, we know how to describe this problem 100% with the mechanics, because we're going to invoke the second law now, because we have to add these forces. If these forces add up to 0, we're going to invoke the first law. If these forces add up to a finite number like 2 or 5 or 17 newtons, then we're going to invoke the second law. We have used all 3 laws. We understand how this problem works, and technically we should be able to describe anything in the future about this object. That is why my initial question was, if we know these 3 laws and we know how to apply them, invoking in this case something called the free body diagram to help us solve things. But later on, of course, we need geometry, and that is why the practice of adding vectors is important. That is why you need trig functions, and the problems in actuality, they involve a lot of math. But the point being is, for us in here, we can understand this problem. And if it's the math that is the hurdle, we just give it to a mathematician and here, solve these equations for us. Now we can describe whatever the future is with this dog sled system is. So that is my point all along. Okay, that is my entire point that I wanted to emphasize on, illustrated by this example. Any example, a car, a bicycle, anything that is involved in mechanics, all you really need is 3 laws of Newton. The third law usually is invoked first, because that helps you isolate the system that you want to study by invoking these actions, reactions, and trying to find the external forces and all of that. Then you add them up. Whatever you end up with, you're going to either invoke the first law or the second law, one of the two. Okay, there is no third laws. And that's it. Then you can solve, for example, somebody gives you a building and tells you, is the building stationary? Okay, can you fix that problem for us? Well, you're going to invoke the third law first and then add up the forces, do the free body diagram, solve for it, and you're done. Okay? Do you guys understand what I'm saying in here about this thing in here? Any problem, doesn't matter. You do something called the free body diagram. How you do that? You invoke the third law. Once the third law basically helps you isolate the system, then it becomes a matter of algebra. If you're good in algebra or not good in algebra, it's irrelevant as far as you're concerned. The problem at that point is outside of your hands as the physicist. Is somebody else who needs to understand it. It needs to handle it for you. Understanding what needs to... Yes, that is usually the challenge. It's very well put, Jeffrey, okay? Sometimes that is the work of the physicist, can be trying to understand what things are. And that is, you're absolutely right. I mean, I probably may have made it too simple in this case by stating it this way. Understanding these interactions and what goes where and things like that, that's really what needs practice. That's why there is a condition. If we know how to apply Newton's laws, and you're absolutely right, Jeffrey, I'm not trying to make it simpler than what it is. So please, I'm sorry if I did that. But if we, and that's why I say if we know how to use the Newton's laws, these 3 laws, technically, we are done. Okay? But I want to invite you to Thursday to answer the question of why we need more than this 3 laws of Newton. Okay? So I'm hoping that you guys will show up on Thursday, assuming that there is something that is going to happen on Thursday that will entice you to go past chapter 6 or whatever chapter we're in right now. Chapter 5. Yes? Okay. Okay, very good. So let's continue this chapter and close the book on it. I don't know what this example is basically. Some more questions in here. Again, this is a representation of the free body diagram. It's asking you questions in here. So you have an ice on a tilted, on a straight surface, and it's asking you as the ramp is raised, which force remains constant. The force of gravity stays constant. That's because you are almost the same distance in here. But the n starts to diminish, because the n, the normal in here that is required, is actually compensating just for this part, not for this one, which is the component as a vector. Component of vector is always less. Now it's compensating for just less. Now it's compensating for nothing. So in this case, the object will go in a free fall. Okay? So the normal is exactly what the doctor needed. So if you tilt the surface in this case, yeah, that's exactly what we do, Kyle. Okay? That's what we do. I mean, our job as physicists stops in stating the problem, physics, and then give it to somebody else. Of course, what happened usually in physics, and that's exactly the story of Newton, there were not enough mathematicians who could do the problem for him, so he ended up inventing calculus. So that's why physicists sometimes are forced to do math, sometimes more math than mathematicians, because invent new mathematics actually, just to solve their own problems. So that's another challenge. But the point is clear, okay? That is exactly what we do. I mean, what we should do, okay? Okay? But the point in here for this rest of these vectors in here, as the surface tilts, less and less of the normal in this case, because again, we're dealing with the components of the force. So if the surface was here, this is mg, the normal needs to be exactly mg. If the surface is tilted now, this is mg, this is the component that mg that the normal has to handle. This one only, not the entire vector. Of course, the entire vector is more than its components. That's why the normal now is less and less. And if you keep on tilting, at some point, there will be no normal because there will be no component for mg. Mg will be vertical. It has no horizontal component at that point. So there is no normal in this case. The object will fall in free fall. Okay? You can actually try this one with a book, for example. And you start tilting it and you put an object. Don't want the phone to fall on things, okay? And the components at some point it's going to be, n will be just enough so that this thing starts to slide, okay? You can do this experiment at home. It's not hard to do. Okay. So again, the same story in here between Nelly. This is the summary of everything. This is in a nutshell, all three laws of Newton that I am saying again and again, that all you really need to solve any problem in physics, in mechanics that is. Okay? So I want you to pay attention to these three laws. Again, the first law says that basically if there is an object and there are no net forces, that object will stay in its rest if it was at rest, or continue moving in the same direction with the same speed if it was moving with the velocity. Now, if the object is under net forces, in this case, the object is going to undergo change in motion, namely acceleration. The acceleration is proportional to force and inversely proportional to the inertia of the object. The third law states that if objects interact, they do so in such a way, if one exerts a force on the other one exerts a force that is equal in magnitude and opposite direction. That's it. That's all the book on the three laws of Newton. Any questions about these three laws now, up to this point? Or the course in general? I know we have assignments, we have things that are due, things like that. No? If you guys don't have any questions, don't forget you have a bunch of things that are second question. The second question that is due today, Jeffrey? Or is there another question that you're talking? I don't understand, Jeffrey, your input. I'm still not sure. If you can't turn on the microphone and say what you want to say, because I'm confused a little bit. Oh, you're asking about that question. What is the minimum amount of items we need to determine when we can start testing? Not sure. I'm not sure. I don't understand the question, Jeffrey. What is the minimum amount of items we need to determine when we can start testing? The last.
The question I had was, when we're testing to see what we can eliminate with the third law, like how many items, like how many factors do we need until we can start testing for zero, or the first two laws of Newton?
Okay, first of all, there is no minimum or maximum, okay? You tally the forces, you add them up. Remember, they are vectors, okay? Just basically, you have to be very careful invoking the third law first before you eliminate external things. If you want to remove the Earth, you have to remember the magnitude of the pull of the Earth and the direction of that force. Once you know that, you draw its vector, then you're done. Remove the Earth from the picture. For example, the friction, the same thing. Once you have all of these forces properly drawn, then at that point you add them algebraically. There is no, it's algebra. You add them with the vector directions that we talked about in previous slides. Whatever ends up in there, if it's a zero, then you know it's the first law. If it's not zero, for example, if I do this building where I am at right now, the house that I am in right now, and tally all the forces on it right now, it should tally to zero. Its weight on the ground, its support, for example, on the sides. There is probably wind on this side. There is maybe support from the stuff on the other side. So I can tally all of these forces. I should find zero. Why should I find zero? Because the house is not moving. Okay. Yep, that's correct. Okay, that's why it should be zero. So in this case, as an architect, for example, building buildings, and I want to build a high rise, I have to deal with a problem that when I tally all the stresses on the building, including its own weights and the wind and all of that, I should have zero. Otherwise, I have a problem as an architect. My building is not stable. But in some situations, no, I don't want zero. For example, when I tally all the forces, for example, on a rocket, I should find it not zero because the rocket is moving. It needs to accelerate, actually, okay? So, for example, if I am Matt Damon trying to get to the rescuers, then in this case, I have to make sure that all of the forces that I am subject to point in the same direction with the proper acceleration so that I reach that point. So again, depending on the situation now, that's where the math is. So that's usually where the details are. But in terms of vectors, once I reach vectors, they can be pointing, and I drew them in 2D. They could be pointing in 3D, actually. They could pointing in all directions that they can. Then in this case, add them up. Wherever their sum is pointing, that is where I go and invoke the first or the second law. Okay? If it's zero, then it's the first law. If it's not zero, then it's second law.
Okay.
Okay?
Yep.
Yeah, of course, we're not going to be doing this a lot, honestly, because it's basically just conceptually, at least you have that. I know some of you probably are going to be in medical fields and other places, so you will have that. But some of you are going toward engineering, I know that. So those who are coming to engineering, they will be sick of these things to the bones because they will do this on a daily basis. Okay? No cameras. Okay, you are not going to be required to do cameras. Okay, so don't worry about that. Although they told us there is no reason why we should, but I don't really feel myself that you have to have basically yourself and I mean, the exam by itself is stress enough, let alone having somebody else watching over your shoulder. So, okay. Yes, you will get the study guides for the exams. Okay. You will be given specifically what basically how to prepare for them. Okay. No problem. Any more questions?
In regards to what V said about the study guide to the midterm, everything, all the material, I get it's gonna cover like the first 18 chapters, I think, or whatever. But basically, all the questions there, are they going to be similar to the exam, or do you advise that we just study everything thoroughly?
Okay, when that point comes in, my thinking is if you have a full understanding of what we're doing in general, okay, you should not have difficulty with the exam. There will be some technical issues, the specific question in here that sometimes sounds to be asking for some, but you will be given the guides enough so that you will do that. Okay, you should be ready for the exams. Okay, you should, in my feeling, you will have enough time to prepare for it. But the thing with this preparations that I think sometimes falters is when people start late for it. Okay, they don't start with it immediately. They don't take it seriously enough. They think, okay, just preparation. I have all of the materials before me. I'm going to start on it. The exam is on Thursday, so Wednesday afternoon I'll do that. That is a big mistake. Okay, that is on Wednesday when you look at it and you realize, oh man, this is too much work. I really needed at least 3 or 4 days to prepare for this thing. Okay, that is when that thing is. Usually it's a good idea for the exam or anything, especially for the exam more so than anything else, to have a comprehensive look at it from beginning to the end, the entire materials, and be at ease with every aspect of it, every angle with it. Now, you discover that there is a problem in this area, that somehow I'm vague about it. That is when the question needs to be asked. You ask me or you go back in the reference and make sure yourself you're at ease with it. When can you do that? If you have ample time to do this. But if you come to the last day and start preparing, that is when a lot of things start coming at that some point, and then you start basically giving up, and it's really more frustrating. So again, you'll be given enough time to review the material. My suggestion is you start on them right away. You have a clear idea, a plan about how to tackle everything. There are some vague areas that you try to revise them. You can find them, ask a question. You have enough time to go about them and clarify everything. Okay?
All right.
Okay. Okay, guys, if you don't have any questions, I know we ended up before time, but again, that's good because we covered everything we're supposed to cover. And don't forget that you're going to go to the discussion immediately and answer those questions. And for those who are not live, they should do it after they watch the video. Thank you. Bye. See you guys Thursday.